My name is Steven, and today I'll be talking about some time-saving tools that we can use in Creo. All right, so Bill Gates once said, "I choose a lazy person to do a hard job because a lazy person will find an easy way to do it." And I really like this quote. I think it's kind of funny. So Bill Gates, one of the most, successful businessmen of our generation, will choose a lazy person to do a hard job because the lazy person will find an easy way to do it. So whenever my wife tells me I'm being lazy, I just go back to this quote and tell her Bill Gates would hire me. No, I think we know what Bill Gates is trying to say with this quote. And basically what he's saying is he wants to hire people to do hard jobs that will find efficient, time-saving ways to do things to get it done fast and efficiently, right? So that we can eventually learn to work smarter and not harder. Okay, so that's what we'll be talking about today. We'll be talking about some tips in Creo that will help you to work smarter and not harder and save you time while you're doing it. All right, so I've set up this presentation today. I'll kind of be jumping back and forth between the presentation and Creo. And basically what we're going to go over is 4 time-saving goals. So the first one is saving time with design. Second one is saving time with annotations and drawings. Third one is saving time with model modifications. And then finally, we'll be finishing with saving time with simulation. All right, goal number 1, saving time with design. So this is the assembly that I'll be working in Creo with today. It's an air cleaning assembly. And we're going to be doing a few different things. So if you take a look at the right-hand side here, we're going to be creating a housing that's going to hold and mount this air temperature sensor to our assembly. And we're going to be using some time-saving modeling techniques, which I'll touch on, and we're also going to be leveraging the multi-body design. And then once we've created that part, we're also going to mount it to the assembly, and we're going to be able to do this very quickly and efficiently by using the Intelligent Fastener Extension, or IFX. So some of the core modeling techniques that we'll be using today, the first thing we're going to do is we're going to be working from assembly mode for a lot of these features. And this is something that a lot of engineers and designers don't do, but it actually can save you a lot of time by doing this so that you can reference some of the geometry within the assembly instead of using, dimensions and trying to match them up with what you're referencing in your assembly. We're also going to be using some time-saving sketch and extrude functions that you may not know about. So we'll be using project and thicken sketch for the extrude while we create this part. Now, before I get into the demonstration, I did want to touch on the Intelligent Fastener Extension, or IFX. So basically what this extension does is it automates the fastener selection, creation, and assembly of whatever we're trying to, assemble together with fasteners, right? So it really does help speed up that process. It's going to allow you to pick from a catalog of what fastener you want to use, and it will also create that geometry with your part and assembly as well. So I'll jump over to Creo. And you can see this is the part that we'll be working with today. This is our air cleaning assembly. And if we zoom into our air temperature sensor here, we're going to be creating a housing that's going to mount this air temperature sensor to our assembly. Okay, so if we take a look at a cross section of this, we're going to be creating some type of part that's going to probably extend up to here from this surface up to our bottom surface of our temperature sensor, as well as create a barrel to protect this sensor as well. So while I'm in assembly mode, what I can do is I can activate any assembly or part that's located in our model tree, right? So I can click on this, hit activate that certain part within my model tree assembly. And from there, we can go ahead and make modifications to that part without leaving assembly So what I have here is this assembly for this air temperature sensor. I've assembled a blank part onto here, and this is what we'll be using to create our housing. Okay. So the first thing I'm going to do is I'm going to extrude the mounting portion of our air temperature housing. So I'll hit extrude, click on the surface here. All right, so now that we're in sketch mode, what I'm going to do is I'm going to hit the project feature. And what we want is we kind of want our geometry to replicate this top surface here, right? So what we're going to do is click on this top surface. And using our project feature, we're able to quickly replicate that geometry uh, that our housing will mount to, right? I'll also use the project for this hole in the middle here. And now we have the geometry that we kind of want. So I hit OK. Now, instead of giving this guy a dimension of how far we want to extrude it, we're actually going to reference um, the top of this air temperature sensor surface that we want to extrude to. So I can do that by going over to depth, to reference, and clicking on our surface that we want to extrude to. Okay. So now we have kind of the base of what our part is going to look like. What we also want to do is we want to add a barrel that's going to protect our sensor portion of this assembly, right? So I can do this from this cross-section mode. Again, I'm going to activate our part, and from here I can go ahead and modify it as needed. So again, I'm going to do an extrude. We're going to do project as well, and we'll just project this surface that I created before. Okay, so usually what people would do from here is they would probably create two circles, right? Two circles with different diameters to create kind of a barrel that goes down. But what I can do is I can actually just leave this sketch as is. And within the extrude function, we can hit thicken sketch. So from here, what it will do is it will just take that circle sketch that we made, thicken it, and make it to the desired thickness that we want. Okay, so it looks something like this. I'll give it a length of 26. And so far our part kind of looks something like this, right? Okay, so now the next thing I want to do is I want to put some type of cover or gate on the bottom of this barrel here of our part. So since we won't be referencing anything in our assembly, I'll go ahead and open up this guy separately. So now that we have our part in here, again, I'm going to just use the extrude, click on our surface, and I'm going to use that thicken sketch function again. So this time I'm going to do a rectangle, something like this. Give it a dimension of 4.2. Hit OK. We're going to have this go down to 1.2. And again, I'm going to use this thicken sketch, and we're going to give it the same wall thickness as the other sketch that we did. Okay. So now we have something that looks like this. Now I want to pattern this to kind of create that gate. So I'm going to hit pattern, and we're going to do an axis pattern. We'll quickly create our axis here. Creo picks it up that we wanted to use that axis. We'll do two members, 90 degrees, and that should create the kind of gate that we kind of want. So now we have a protective gate that's going to protect our sensor, but also allow air to come through and contact that sensor as well. Okay. So now what I'm going to do is I'm going to leverage some of the multi-body function that comes with Creo 7 and on. Okay. So basically what I want to do is separate this barrel and this mount portion of our housing and give them two different materials. And Without using body operations here, it might take a little bit longer, but we're going to save some time by creating two different bodies to do this. So I'll go over to our body operations and I'll hit split body. Select our geometry here, and we're going to use this surface as our splitting surface. We'll hit OK. So now if we go over to our design items, we can see that we have two bodies. The first one is kind of this mounting portion, and the second one is this barrel. Okay, so I'll just rename these to what I want them to be. I'll just say mount for the first body and barrel for the second body. Okay, and then the final thing I'm going to do is I'm going to give these two different appearances so we can easily see the difference of them. Okay, so now we have our part. It could look something like this, right? Everything looks good, but now what we want to do is we want to set different materials to these two different bodies. And I can do that very easily by going over to our bodies, right-clicking and hitting Assign Material. And we're going to be working with some different plastics here. So I'll hit, we'll do, I don't know, EP for the first one. And for the second one, we'll just give it another plastic material here. Okay. So just like that, we were able to create a part very quickly, leveraging some of our cool sketching and extrude functions. And using our body operations, we were able to split up these into two different bodies and assign different materials to them very quickly and easily. Okay. So now the next step of this housing, creating this housing, is actually assembling it to our air cleaning assembly, right? And what we're going to do for that is we're going to leverage our intelligent fastener extension. So if we go up to Tools and Intelligent Fastener Extension, we're going to put on a couple screws that are going to mount this housing to our assembly. So I'll hit on Screws, select our axis and our top and bottom surfaces here. So once we're into this extension, it's going to pull up this screw fastener definition window. And from here, we can choose, what catalog we want. We can choose what type of fastener we want to use. For this case, we're going to use this one right here, this ISO 4762 8.8. IFX also allows us to put in washers, and we're going to do that as well. All right. It'll give you this 2D preview of what it will kind of look like. It'll look like something like this, and this looks pretty good. So we'll go ahead and click OK. Now, what IFX does is it realizes that I have two axes on this assembly that are kind of referenced to each other and are similar in a way. So it picks up on that and says, do we want to assemble the fastener on all instances? So we're going to hit yes, because of course we want to add that screw to the other side as well. All right, and just like that, we have our assembled housing to our larger assembly, right? You can see just how quickly we were able to do that. And this IFX extension would be super useful if you had to do a fasten, a bunch of parts to a very large assembly. You'd be able to save a lot of time by using this IFX extension. All right. All right, going back to our PowerPoint presentation here, we're going to move on to goal number 2. Goal number 2 is saving time with annotations and drawings. So what we're going to be doing now that we have this part, we are going to be creating a drawing for this housing. So we're going to be doing this very quickly by using some custom drawing templates, which I'll talk a little bit about. We're going to be using the automatic model annotations. And then finally, we're going to be creating some geometric tolerances for this guy as well. And to do that very quickly and easily, we're going to be using our GD&T Advisor extension. So before I get into our presentation, I did want to talk a little bit about this extension. Um, so basically what GD&T Advisor does is it simplifies and speeds up the creation of semantically correct GD&Ts. So there's a lot of baked-in features with GD&T Advisor. It's going to, propose to you the correct geometric tolerance to use based on what your feature is and how it's on your part. It's also going to provide you with validation. So there's this thing called an advisor tree that's going to give you warning and error messages if you have um, any geometric tolerances that kind of don't make sense. And then it's also going to provide you education. If you have these error or warning messages, you can ask for help, and it'll explain exactly why it's advising you to change those accordingly. All right, so I'll jump back over to Creo here. And the first thing that we're going to do is we're going to open up our template that we're going to be using for this part here. So if I open up my template here, we can see that we have views that I've put in here. So I know a lot of companies and engineers use templates within their system, but one thing they don't do a lot is putting in the views. Now, if you have a part that's very similar, um, you know that the views are going to be, shared among that certain series of parts, you can actually just put these views in here to save you time of actually creating those views themselves. And then another thing that I put in here was a custom table from the Creo quick tables. So a lot of people don't know about these as well. We do have these Creo quick tables that bring in certain parameters that we want to see within our drawing. For this example, we put in this table here that shows the body name, body material, and any notes associated with those two bodies. Okay, so we'll close this out, open up our part here, and create our drawing. So we're going to browse for that template that we created. And by using this template, you can see that we've brought in the views that we want to see with this part, as well as this table that we added shows the body names and materials of that part that we created as well. Now, if you've worked in Creo, you probably know that we have this option to um, annotate through model annotations. This is something that will save you a lot of time. So if you click on any view, it will actually bring up the dimensions that you use to create this part, right? So we can click on whatever ones we want to see, right? So we click on these two, and it brings those in automatically. We can do the same thing up here. So we'll add, I don't know, this guy, this guy. You'll actually see because we use that thickness extrusion, instead of giving um, two different diameters of the circles, it'll actually say, okay, we have this circle with this certain diameter, and it's this wall thickness right here. So Creo realizes that, and it puts it in the model annotations for you. All right, so now what we're going to do is we're going to add some geometric tolerances to this part. So traditionally what I do is I'd go up to geometric tolerance, create them in here, but the fastest and easiest way to do this is by using the GD&T Advisor extension. So I'll open up our part here, and we can go over to Applications and GD&T Advisor. So now that we have our part, our feature tree and our advisor tree. So our feature tree is going to show what features we have geometric tolerances for, and our advisor tree is going to tell us if there's anything wrong with those geometric tolerances that we created. So we'll go ahead and create a few geometric tolerances here. So GD&T Advisor will pick up the feature that you selected, and it will automatically suggest which geometric tolerances make the most sense for that certain feature. So it's saying that because we picked this top surface here, it wants us to use flatness because that will be the highest level of um, highest level of constraint for that geometric tolerance. We'll give it a value. And then it's going to ask us if we want to do a datum feature, and we'll say yes, we want to create a datum feature A. Okay. So just like that, we were very easily able to quickly create this geometric tolerances. So we're going to create a couple more here. I'll do one on the bottom surface as well. This time it's suggesting that we do a profile, so we're going to use that. Give it a tolerance, and suggesting that we don't create a datum feature for this one, so we're going to go ahead and leave that just as is. So now we have our two geometric tolerances, and we're just going to add a few more here. So I'm going to do one for this hole. This time it's saying we should use the perpendicularity, so we'll do that. Give it a tolerance here, max material condition, and create another datum. So now we have something that looks like this, and we'll just do one more for this final hole over here. This might be kind of overdoing it, but I just did want to show you how GD&T Advisor works, how it suggests the correct geometric tolerances for your part. So this time it's suggesting that we do a position. So we'll give it a tolerance again, and we'll say max material condition. We don't want to create a datum, so we'll hit OK here. So just like that, we were able to create these geometric tolerances very quickly with those automated suggestions from GD&T Advisor, right? Now, if we look at our advisor tree, we'll notice that we have some orange exclamation points and then some red X's. So these exclamation points are warnings, and these are errors here. So these are things that we need to change, or these red X's. Now, what it's saying is that a zero value tolerance is not allowed if we have a hole with a geometric tolerance with a specific tolerance here. So what we can do is click on this, go ahead and give it some type of tolerance, and if we hit regenerate, that error will go away, right? Now, if we want to know why a zero value tolerance is not allowed, we can click on that error message, click on more help, and see exactly why. It'll tell you, according to the ASME rules, right, this is why we need a tolerance value on this geometric tolerance, okay? All right, so we have our geometric tolerances, we have our datums, we were able to very quickly and easily create them. So I'll go back over to our drawing, and again, using these model annotations, we're able to pull these geometric tolerances in very easily and quickly to show them in our drawing, right? So now we have something like this. Okay, so those are some of the tips and tricks of saving time with drawings. So I'll go back to the presentation and we'll start talking about a few other things. All right. So we've saved time with modeling, we've saved time with annotations. Now it's time to save time with modifications. So what we're going to be doing is we're going to be bringing in actually a SolidWorks part that we suppose we got from one of our suppliers or something, and we're going to very easily be able to convert that to a Creo part. We're then going to modify this part by using flexible modeling to quickly modify the geometry of what we're trying to do. Okay. All right, so we're going to be putting a vent, a SolidWorks part vent, on this protrusion here. So what I can do is go to Model, Assemble, go to my SolidWorks part, and open them up here. I'll quickly assemble this guy to this geometry. So we have something that looks kind of like this, right? Now, what we want to do is we want to extend this flat portion here. So we want to extend this geometry, this end here, and bring it out kind of in the X direction here. So again, working from assembly mode, I will go ahead and activate this part here. And you'll notice that Creo picks up this is a SolidWorks part, right? It knows what type of file it is, and it works with this part to bring it into the assembly. Now what we're going to do is go over to flexible modeling, and we're going to use the move function. So as soon as I click on this, it asks me if I want to convert this SolidWorks part to a Creo part. We're going to hit yes. So we'll hit yes, and now it has converted our SolidWorks part to a Creo part, so we can go ahead and create Creo features with this part. What I'll do now is go back to our move. First thing I'm going to do is kind of click the geometry that I want to move. And now it's going to ask me for my origin. We'll just say that the origin is this surface here. So like I said before, we wanted to extend this out. So all we have to do is just drag this guy out. And what flexible modeling will do is it will modify that geometry and create that extension without having to go into the specific features that created it, and very quickly and easily be able to modify that geometry as we wanted it to. So flexible modeling basically is a quick and easy way to modify geometry if you want to extend or move anything with your part very quickly. All right, on to our final goal. So this has to do with saving time with simulation. And in this part of the demonstration, we'll be using Creo Simulation Live. Now, for the first three goals, we use some techniques that might save us, hours, minutes, hours. But using Creo Simulation Live will save you time and money throughout the entire design process, right? Basically, the purpose of Creo Simulation Live is to be able to use simulation more early and often in the product development process, allowing you to be more confident in your design, save money, save design time throughout the entire process. And so we're going to be working with this portion of our assembly here. And basically what it is, it's a 3D model part, and it's kind of like an air vent. So we're going to be making some design changes to this geometry, going back to our simulation and seeing how those design changes affect our simulation. Okay. So before I get into this portion of the demonstration, I did want to talk a little bit more about Creo Simulation Live because I really think it's a great tool. So basically what it is PTC partnered up with ANSYS, and if you know anything about simulation and engineering, ANSYS has been the global leader in the last 50 years. And basically, what they wanted to do was create a tool that was very user friendly. Maybe not the most accurate simulation tool, but something that engineers can very quickly and easily use while they're designing their products to make sure that their design, is heading in the right direction earlier in the process, right? So CSL is a powerful linear solver that rapidly defines and performs linear analysis for not only parts but also large assemblies. Okay, and we're able to do simulation for structural, thermal, modal, and fluid analyses. A big part of CSL is that it's a meshless environment. So if you've worked with simulation, you probably know that setting up your model for simulation is probably the most difficult and time-consuming part. Whether that's creating your mesh, creating your contact points, defeaturing your model so it doesn't break, getting rid of small holes and interferences. All that is very time consuming, but all of that can be thrown out the window while using CSL because of this meshless environment, right? And because it creates that automatic volumetric mesh, it's not the most accurate, but we can really use this and leverage this tool to make sure our design is heading in the right direction. Also, CSL, the results are instantaneous. So you'll see as I do the demonstration here, as we make design changes, as we simulate our constraints and loads, we have a solution within seconds, right? Which is very nice. And also these results are interactive. So as soon as you make design changes, change up the model, you're able to see how those design changes affect your simulation very quickly and easily. And the way it does this is, so Creo Parametric runs on your CPU or your central processing unit on your computer, and CSL works on the graphics card. So because of that, they're able to work simultaneously and give those instantaneous results to you. All right, so I'll jump back over to Creo here. And like I said, this is kind of the part that we're going to be simulating, okay? So I'll go over to live simulation. And since we're only going to be working on this part here, I'll set up a scope. So in the simulation, to make it run a little more quickly, what we'll do is we'll set up this scope to include these two parts here so that we're not bringing in anything that we don't want to. From there, I will set up my loads and constraints. For this specific one, we're just going to be doing a structural study. So I'll just put in some simple constraints and loads here. So I'll put a fixed displacement on this guy, and we'll put a load on this surface of 100 newtons in the z direction. All right, so now we have something that looks like this. We're good to go with our constraints and loads. So now all we have to do is hit the simulate button at the top here and see our results. All right, so within a matter of, what was that, like 3 seconds, we have our solution, right? We have our, in this case, we're looking at the von Mises stress. And what we're going to try to achieve is, reducing this and seeing, if maybe if we change up this part here, we add some lattice structures for 3D printing, how that affects our von Mises stress, right? If we wanted to look at the deformation of this, we could also do that. If we wanted to animate and see, kind of an exaggerated view of how this thing is deforming, we can also click on the animate deformation button as well. But like I said, today we're going to be looking at the von Mises stress. And since I'll be making design changes and I'm kind of concerned about the maximum von Mises stress, what I'm going to do is I'm going to set up a simulation probe. But the first thing I want to do is figure out where this max point of stress is, right? But before I do that, I did want to show that we do have the option of performance options with this simulation. So if you click slider that you can choose between speed and accuracy. For this demonstration, we'll maybe notch this up a little bit more for the accuracy, and we can close that guy out. So we're concerned about the max von Mises stress, right? So we want to know where that is happening. And it looks like if we click on our icon here, our max von Mises stress is kind of happening on this surface. So what we'll do is we will set up a simulation probe, and we'll do maximum on that surface. And then we'll go ahead and save it. Okay. So now it has our probe on here. And since we're going to be making design changes, I'm going to want to accumulate this data. So I can click on Query and Accumulate Data. And now when I make design changes, it will bring up this kind of bar graph view of how our stress changes as we make those geometry and design changes. Okay. So one of the things that I'm going to do is I'm going to change this surface into a lattice structure. Maybe we might be able to, save some material by turning this top part into a lattice structure and reducing the costs of our part. So from this CSL mode, this assembly mode, I can again activate our feature here. First thing we're going to want to do is edit this extrude to get rid of this surface right here, this feature. Okay. Now that we have this, we can go ahead and put in our lattice structure. So I'll go ahead and click on our intent edges here, top and bottom surfaces. And for our first cell position, I've set up a point kind of in the middle of this guy to set up our lattice structure. We're going to be doing a formula-driven lattice structure. And I guess we'll start out with maybe a diamond function. And for our cell fill, we'll do 1.25. Okay. So I'll have something that looks like that for our lattice structure. And we can hit OK. So our lattice structure looks something like this. But we want to know, now that we've made this design change, we want to know how that affects our simulation, right? So what we can do is go back to our live simulation. Let this guy run for a few seconds here. And then if we go back into our probe that we set up, as it loads here, you'll be able to see how that design change affected our stress. And actually what we're seeing is we were able to reduce that stress. So that's huge, right? We're probably saving in material here, and we were able to reduce that amount of stress by putting in that lattice structure. So that's awesome, right? So let's make a couple more changes here. I'll go back to my part, and let's try maybe a different type of lattice structure. So we were doing diamond before. Let's go to gyroid and see how that looks. Okay, looks good. We'll go back to our simulation here. See how this looks for our von Mises stress. Give it a couple seconds to load. And you can see how that design change affected our von Mises stress as well. So it looks like by putting a lattice structure in here, not only will we save on material, but we'll also save on stress in this part, right? Which is huge. So basically CSL will save you time in As long as you utilize CSL earlier and often in the design process, you're really going to have a good idea of whether or not your design is heading in the right direction, right? There's one more thing I did want to show with CSL, and that is leveraging some of these analysis tools. So what we can do, let's say we wanted to change our wall thickness in our lattice structure, um, set up an analysis and see how those changes, if we maybe vary that wall thickness, we'll see how our stress changes if we vary that wall thickness, right? So what we can do is set up a sensitivity analysis. So I'll hit on dimension and pick that cell wall thickness over in our model. We'll go with the recommended variable range. Maybe we'll do 5 steps. And then our parameter that we want to analyze is indeed our max stress, right? So this does take a few minutes to load. What I would do is I would hit compute. It would come up with this chart here. So what I've done is I brought up this sensitivity plot that it spits out. So we can analyze this by saying, okay, right now we're at 1.25, right? If we change our wall thickness within this range, we see that the stress does vary a little bit. So if we wanted to optimize this, we'd probably bring this down to something like, I don't know, 1.375, right? So you can utilize and leverage these analysis tools while you're doing your simulation to even further pinpoint, what you're trying